Welcome to Colloquium. We're pleased today to have with us Professor Lixing from the University of Michigan at Flint. He's visiting our department at large, but also our colleague Jianheng Xu. He'll talk with us about, no, I didn't ask him how to pronounce this, the Nelder Mead Simplex algorithm, the effect of dimensionality and new implementation. We look forward to hearing what you have to say.
Thank you. Good afternoon. It's my great pleasure to talk here at the SIU. Thanks for inviting me and for attending this talk. Yes, my topic today is Nelder Mead Simplex method. So here's our problem. We consider to minimize a multivariate function f of x. So here the function we call f the objective function of the problem. We assume it is continuous, but its derivatives are either unavailable or too expensive to compute. So we cannot rely on some efficient algorithms using derivative information. In this case, a non-derivative method or derivative-free algorithm is often used to solve the problem. So what are the derivative-free methods? They do not use derivative information or even attempt to approximate derivatives, like using finite differences. We don't even try that. Since the 1950s, there have been many derivative-free methods proposed. Among them, one of the most widely used method is the simplex method of John Nelder and Nelder Mead. They proposed their algorithm in 1965. By the way, don't mix this method up with the famous simplex method for linear programming. They're totally different. This is a picture of John Nelder. John Nelder, he was a British statistician. He made many important contributions in computational statistics and statistical theory. So let me first briefly introduce this method. So starting with the simplex. So in dimension 2, a simplex is simply a triangle. So the dots here, we call them vertices. This is dimension 3 simplex. We have a tetrahedron. So in general, a simplex in Rn is a geometric figure that is the convex hull of n+1 vertices. Here is the idea of the Nelder Mead method. It's quite simple. So this method iteratively generates a sequence of simplexes, which hopefully the sequence will convert to a minimizer of the function. In each simplex, remember we are talking about Rn, so we have n+1 vertices. So we will sort them based on the function value while minimizing the function. So we zero the best. We sub n the worst vertex for the simplex. Now, at iteration k, this method has one simplex at hand. So it will generate the next simplex. So it will use one of the four operations: reflection, expansion, contraction. We have two kinds of contraction and shrinkage. So here is reflection. So this is our current simplex, the best vertex, the worst. Okay, this one is the center of these two vertices. Now we construct a reflection point R, a reflection of that triangle, that simplex. Then we compare the function value at R and the function values at those vertices. If this vertex is better than this, but not as good as this, of course better than this, and then we'll use this simplex as my next one. Remember, we're generating a sequence of simplexes, so each time we generate a new simplex. Okay. If after constructing the reflection point, we found that this is even better than the current best one, it means possibly if we go along this direction, we get even better one. So what the simplex method does is to construct the so-called extension point. We call this E. And then we compare this E and the first obtained R, the reflection point. If this is better than reflection, then this will be my next new simplex. If not, if this is better than that, we keep that, keep the reflection simplex as my next simplex. What about if my reflection point is worse than this, but better than this one? So the simplex, the Nelder Mead method will construct outside contraction. So this triangle is smaller than that one. So, and then we compare this with this one, with the reflection. If this is better than this, this will be my next simplex. If not, so we need to do something else. I'll keep that for a moment. What about if we found that this reflection point is even worse than the current worst one? So possibly we won't see a better one here. So maybe in this area. So what we do, we construct the inside contraction, and then we compare these two. If this is better than the current worst vertex, this will be my next simplex. Okay, if all this fails, so far let's summarize. So this is our current simplex. We wanted to replace it, particularly replace the worst vertex by a better one. So we have four options: reflection, extension, outside contraction, inside contraction. If all those fails, then we carry out the next step, which is called shrinkage. So it's possibly this triangle is too big, so we cut it, so we shrink it to a smaller one. So hopefully we get using this new simplex, we'll be able to move on to get a better approximation later. This is a summary of the Nelder Mead method in general Rn. If we look at the formulas here, we see four parameters: alpha, beta, gamma, and delta. In order to implement this method, we need to specify them. What are their values? Actually, there are different choices. In the standard implementation, this one is used in Matlab's FMINSEARCH. This is a built-in function in Matlab. The parameter values are chosen as alpha equals 1, beta equals 2, gamma equals 1/2, delta equals 1/2. What are they? Alpha is basically related to reflection. So basically this long over that long is alpha. So basically we're saying they have equal length. Now beta is related to extension. So this long from the center to E over from the center to the worst one. So in standard implementation, this is about double the length of that one. Now gamma is for contraction, so this is about half long side, and this is about half long side. Delta is for shrinkage, so this one cut half, a smaller simplex. here is a very simple example to illustrate how this Nelder Mead method works. So basically, this is a so simple quadratic function. We know the answer. So the minimizer is around 0, 0 here, right? So we start from this simplex. So using Matlab, FMINSEARCH, I created this sequence of simplexes. Eventually, after about 80 iterations, the Nelder Mead method found was able to locate the minimizer with the function value something like 7 multiplied 10 to the negative 10. Remember, the minimum value is 0 here, right? Very good after on 80 iterations. Like any numerical algorithm for optimization, we are certainly concerned the convergence of Nelder Mead Simplex method. So, will this method always converge to a minimizer of the problem? This turns out to be a pretty challenging problem. Remember, this method was proposed in 1965. Only in 1998, these 4 experts proved some convergence results, focusing on low dimensions, dimension 1, dimension 2. So they assume the objective function, the multivariate function, is strictly convex with bounded level size. Under this assumption, they proved these results. So I'm going to summarize these 2 results. When the dimension is 1, so minimizing a single variable function, right? So we can sometimes we do it in calculus. And remember, now we don't have derivative information. We don't even try to solve f prime x equals 0. So they proved in this case that under the assumptions here, the Nelder Mead method does converge to the minimizer, because for a strictly convex function, we have a unique global minimizer. So that's good news. And when dimension is 2, what they were able to prove in that paper is the Nelder Mead simplex diameters converge to 0. The simplex gets smaller, smaller, smaller. But this does not automatically mean the Nelder Mead method will converge to the minimizer. It might circle around or outside the circle. So this is not really a convergence yet. These are the 2 main theorems they proved in that important paper. This paper is very influential. Very recently, so like Arias, Poonen, and Wright, they proved a new result. So when for n equals 2, dimension equals 2, under the same assumption, they proved that the restricted Nelder Mead method converges to the minimizer. In the restricted Nelder Mead method, we don't allow expansion step. Remember, we have 4 operations: reflection, expansion, contraction, and shrinkage. We have in this restricted method, we have no expansion step. Under this situation, they were able to prove convergent results like this. Okay. So that's good news. We do have some convergence results. Like anything else, we have both good news and bad news. So I talked about the good news first. So here's my bad news. So for dimension bigger than equals 3, we don't have any similar convergence results here. Open. Actually, even worse news, we don't even know if the standard Nelder Mead method always converges to the minimizer, when the objective function is the simplest possible nonlinear function, x1 squared plus x2 squared. We don't know. That's still open. Even worse, we have some non-convergence results discovered. This is a famous example constructed in 1998 by McKinnon. So this function is defined here. It is strictly convex with continuous first derivative, but not continuous second derivative. It's a piecewise defined. So this is the contour. If we start using this simplex, the Nelder Mead method will repeatedly use inside contraction. Eventually, the simplexes will converge to this point, 0, 0. But for this function, 0, 0 is not even a stationary point. This is the minimizer. This is nothing. So this is a failure case, a famous example constructed by McKinnon. Here is another non-convergence example. This is a quartic function. This is not convex, but this has a bounded level sign. Okay. We have two minimizers, here and here. Okay. Now if we start from this simplex, again, this Nelder Mead method will repeatedly use inside contraction. Eventually, the sequence of simplexes will converge to this line segment. This line segment contains no minimizer at all. Here we have a minimizer. Here we have a minimizer. So this is another failure example.
So how about if you choose the simplest covered in big enough?
Yeah, that will be a different situation. I'm talking about for this really particularly chosen simplex. If you choose something like that, I'm pretty sure it will converge. This is for counter examples. Once you have you see some failure situations that already put the counter example.
Finally, is there any strategy you can choose a pretty good initial simplex?
That's a research question. I mentioned that at the end.
It pretty much depends on your initial choice of the simplex.
It depends.
Right.
And other things.
Right.
Other things. Okay. So we have pretty bad news about the convergence, theoretical convergence, right? In theory, but in practice we have a lot of good news. I've already mentioned that this is one of the most popular derivative-free methods. It is widely used in many applications. Look at the citations. I checked today, Google Scholar. The Nelder Mead paper has been cited over 15,000 times. Just based on Google Scholar. This method has been implemented in Matlab as FMINSEARCH, a regular function, in Matlab, Scilab, and some other packages. And particularly, this method has been recommended for solving optimization problems with noisy objective function. What about if you cannot measure your objective exactly, right? Your objective function subject to some noise, then this is recommended method. So that's really good news. So in theory, we have some negative results, but in practice we have been hearing here all good news here. Let's look at what Dion Nelder, one of the two fathers of this method, what he said about this method. This is a quote. Mathematicians hate it because it cannot prove convergence. Engineers seem to love it because it often works. This statement is pretty accurate. Actually, that's the case. So we do have, so mathematicians or engineers have a disagreement here on this. However, they do agree on one thing. So this method can be stagnant or very inefficient when the dimension n gets much higher. If your dimension n equals 2, 3, 4, 5, this is like John Nelder said, so it often works really well. But if your dimension goes to 10, about 10, 20, then you get to see some new problems. Here is one inefficient example. Similar one, right? Standard quadratic. So n is the dimension. So I run FMINSEARCH, the Matlab implementation of the standard Nelder Mead method using those parameters in the program. So when dimension n equals 32, this number is moderately large for the derivative-free optimization method. It's not too big, but it's not a tiny one. Then after about 200,000 iterations, the Nelder Mead method was able to find approximate solution with the objective value 6.7 multiplied 10 to the negative 8. Remember, the minimizer is the minimum value is 0, right? Okay, so but inefficient is that we need so many iterations. We need to use to compute so many function values to get there. When dimension is 32 for this standard quadratic function. Here is a stagnant example. This is a famous the famous Rastenbrock banana function extended version. This is a cursive function. The minimizer is here, minimum value is there. So I run when dimension n equals 18. I run FMINSEARCH. After 1 million iterations, the found objective value is still 19.8, very far away from the minimizer, right? So I tried more, many more iterations. I cannot reduce this much. But this is a stagnant situation, so essentially cannot find the minimizer using the standard Nelder Mead method. So this motivated us to study the effect of dimensionality on this particular method, because we discussed the limited convergence results we have. So we decided to focus on this function. We know Nelder Mead is inefficient when n is high here. We already illustrated that. For this standard quadratic, we use its minimizer as one of the initial one vertex of the initial simplex. So this is because this is the minimizer according to Nelder Mead method. This vertex will remain as the best vertex throughout all the iterations. We have special choice of the initial simplex. According to Lagares, I thought in this case the Nelder Mead method will only use 3 operations: reflection, outside contraction, or inside contraction, no expansion of Schumpeter steps. They have proved this in 1998. So what we did, we investigated the effect of dimensionality on the rate of convergence of the Nelder Mead method in this case. Okay, let's define the rate of convergence. So at iteration k, we have a simplex as k. Remember, this is always the best vertex. We have n other vertices for the simplex. And so this is not the diameter. So we define, we call this oriented line. This is basically, in this case, I'm defining, doesn't matter how big this simplex is. So this is the origin here. Now this and that. We have 3 edges. we find the maximum one among them. This is defined as original length of this simplex in the R3 case. So we have that in Rn. So of course, if this sk goes to infinity, if this sigma sk, the limit is 0, we know the simplex will converge to the origin. This is the minimizer of the finite function. Now here's our rate of convergence definition. So basically, this is a limit superior of, this is the geometric mean of reduction in original length per step. We take the geometric mean here. Based on this definition, the closer the rate to 1, the slower the convergence, based on this initial definition. Here, f0 is the initial simplex nth dimension. We want to study how the rate of convergence depends on Sn, the n, the dimension here, effect of dimensionality. So in the analysis, we study the behavior of Nelder Mead method when one type of operation is used repeatedly. Remember, in this situation, we have only 3 operations reflected inside contraction, outside contraction. We use one of them throughout all the equations to do the analysis. We also assume the worst vertex will be replaced by a new vertex using one. If we repeat using, for example, inside contraction, the new vertex will become the second base in the next simplex. The reason is that we have been using this origin as one of the vertices. This is always the base, so that we get the second base. In this case, we can write the vertices in this form. So essentially, in the next simplex, this one, the worst one, will be replaced somewhere here. This is the second base. This is the base, the second base to the worst. Next step, this one will be replaced by the second base. Will be somewhere here, a new one. Well, turns out under this assumption, the vertices will satisfy an equation we're quite familiar with. This is a recurrence equation. So we have 2 parameters, and they depend on what operations we use. If we use outside contraction, then n will be 3 over 2n b equals -1/2. Now, if we always use inside contraction, we have different AB values. If we always use reflection, we have different A and B values. If we look at this recurrence equation, this is the degree n order n recurrence equation. This is also a linear constant coefficient, so we can say something about this. So to study the behavior, we are going to study the behavior of those vertices. So they satisfy this recurrence equation. So we know because this is a linear with constant coefficient, so its characteristic equation is important. This is characteristic equation for this recurrence relation. This is a degree n polynomial of mu. So it will have n roots. We call them the characteristic values. Now, according to our knowledge on recurrence relations, when k goes to infinity, the behavior of vertex vk and then the simplex method simplex, the Nelder Mead simplexes have those characteristic values, particularly those with the largest modulus, because we are talking about the asymptotic behavior. Okay. So I just mentioned that the characteristic values are important. So how about study their properties? So in a joint paper with Mickey Neumann and Jiang Gong in 2003, so we proved this result. So let mu sub OC and mu ICN and mu RN be a root of any root of the characteristic equation for outside contraction, inside contraction, or reflection respectively. Then we have for the outside contraction, the modulus of this value is always 3 less than 1 for any n, and similarly for inside contraction. But for reflection, this is always 1. For any root, this modulus is always 1. Okay. We also prove the limit. If we let the dimension n goes to infinity, both will converge to 1. So this, remember we have a recurrence relation. The behavior of solution, the vertices, depend on the characteristic values. Because these two properties and this one, this is always 1. The limits are 1 here. So this already indicates as n gets higher and higher, VK, the vertex converts to 0, gets slower and slower because they are the characteristic value gets closer to 1. So this already shows perhaps the rate of convergence will suffer when n gets higher. So in order to see how the rate of convergence suffers as n gets higher, so we did some numerical computation. So here we first calculated the largest and the second largest moduli of characteristic values of inside contraction and outside contraction. For outside contraction, we denote them by LOCN and SLOCN, the largest modulus, the second largest modulus. Similarly for inside contraction, largest, second largest. And then we computed their values for different n dimension n values from n from 3 to 100, together with the rate of convergence. So we have this plot, the rate of convergence plot. So this solid line is the rate of convergence. Remember, the closer to 1, the slower the rate, right? Now look at what happens when n equals about 30, about 32. This value is already about 0.9912, very close to 1. So somehow this explains why when the dimension equals 32, earlier I discussed the inefficient example when n equals 32, that's a quadratic function. For that quadratic function, the Nelder Mead method was quite inefficient. Now the rate here is about 0.9912. As n gets higher, the rate gets closer to 1. It's very close to 1. So this is the plot of rate of convergence. We have some conclusion about the effect of dimensionality on the Nelder Mead method. So as the dimension gets higher and higher, the rate becomes closer to 1. Therefore, the Nelder Mead method makes less and less progress per iteration towards the minimizer. So it gets slower and slower when the dimension gets higher and higher. We would expect the limit of the rate of convergence as n goes infinity is 1. But this is open. But this, from the figure, we conjecture this is the case. The limit will get towards 1. So we do have some understanding now the effect of dimensionality on the behavior of the simplex method. This explains why the Nelder Mead method deteriorates as the dimension gets higher. But we somehow were not very satisfactory in the sense, remember in the previous analysis, our function, our objective function, is this standard quadratic, right? That's very special. And also remember, we use its minimizer as one of the initial vertices. In general, if you are given a function, the problem here is to find it one of its minimizers. So unlikely you keep it as one of the vertices, right? As the initial simplex. So recently we relaxed these two assumptions. So basically we consider the objective function to be uniformly convex. So this function is uniformly convex. Think about a function whose second derivative function is partially definite, and its smallest eigenvalue is bounded below by a partial constant. In that case, we have a uniformly convex function. This one is, of course, uniformly convex, but we have many more. And we start arbitrary initial simplex. So under these new assumptions, so we got some new discoveries. So what we found for the standard Nelder Mead method, the extension set, the inside contraction set, the outside contraction set produce good reduction in the objective function. But then good steps, to put it in a simple sentence, but not the reflection operation. In simple sentence, reflection is not good operation. Okay. Unfortunately, as I'm going to illustrate, the standard Nelder Mead method uses too many reflection steps. This somehow also explains why the Nelder Mead method may become inefficient. We also found using larger simplex, a larger simplex will have decreased the objective value. So large simplex is helpful. So some new discoveries here. Here is a plot about fraction of reflection steps used in the standard Nelder Mead method on this particular quadratic function. The dimension here. We can see that when dimension is small, we only maybe use 30% vertex and 50% reflection steps in the standard Nelder Mead method. But if n gets bigger, let's say 20 or higher, we use the standard Nelder Mead method uses over 90% reflection steps. So this perhaps causes the inefficient behavior of this method. Okay. Last, I would like to talk about a new implementation of the Nelder Mead method. In order, we know now the dimensionality affects the performance of the standard Nelder Mead method a lot. So So in order to tackle this issue, so we propose a new implementation which takes the dimension of the optimization problem into account. Actually, the implementation is pretty straightforward. Here is the standard implementation. We have 4 parameters: alpha equals 1, beta equals 2, gamma equals half, delta equals half. Now, in the new implementation, these parameters relies on the dimension of the problem, not for alpha, the reflection parameter, but for expansion parameter, this one replaces 2. For contraction, this one replaces 1/2. For shrinkage, this one replaces half. Now remember, I discussed that large simplex is helpful, right? Now if we use, for example, this is the shrinkage step. Essentially, we cut the simplex address by half. We get a much smaller one. Now, in this case, think about when n is big. This we only reduce the original simplex by a little bit, not much here. Similarly, for contraction here, if n is large, this is close to 0.75. It's better than half to keep the simplex larger. For these 2 implementations, if dimension n equals 2, they are identical by this choice. But they are different if dimension is higher. Okay. To see if the adaptive parameters are helpful, so we let's look at this function again, the standard quadratic function. Now, using the new implementation, now this is the fraction of reflection steps against the problem dimension of this function. We can see we no longer use 90% of reflection steps. So here we use at most 45%. So this is the indicator. Perhaps this new implementation will perform better. So really, so let's see. Like any other numerical algorithm, we often test a new algorithm on some standard test problems. Here's one. This is a quartic function. D is a diagonal matrix. This is partial definite. This B is a partial definite matrix. So this is the quartic term. This is quadratic term. This epsilon will affect the condition number here. The larger the epsilon, the byte condition here. And this is how far this sigma parameter controls how far away this function from a quadratic. So this is a famous test function introduced by Byrd Nocedal-Zhu in 1990s. So let's compare the 2 implementations. This is the standard implementation. This is the new implementation. Dimension from 10, 20 to 60. This is a quadratic case. We choose epsilon equals 0.05, sigma equals 0, so the quadratic case. Now, this column is the number of function evaluations when this guy terminates. And similarly here. And the final found objective value by this method, and here by that method. Now, for this function, apparently the minimum value of this function will be 0. So the closer to 0, the better the solution. Okay. Now, look at the number of function evaluations. Look at starting from dimension 30, the standard implementation, we see some problem here. Look at the number of function evaluations we need. Has higher, much higher, over 500,000 here. But the found objective value is about 12.6. But for the new implementation here, in this case, after about 20,000 function evaluations, we get the final objective function value 6.9.10⁻⁸. We are quite close to the solution. We got a very good approximate solution. Now if we look at quartic case, we let sigma equals 0.01. And the standard implementation, we can see we get stagnant kind of. We terminate at a pretty deep objective value. We're still far away from the solution. But if you look at the adaptive, the new implementation for each dimension from 10 to 60 here, 10, 20, 30, 40, 50, 60, we can see we get, in each case, we get quite good approximate solution here. Just look at their objective function values. We have reasonable number of function evaluations needed here. So this table seems to indicate that the new implementation is quite promising to handle higher dimensional cases. But one example does not say too much, because maybe this example is just too suitable. Is suitable for this, not for that. So what we did, we tested 11 more standard test functions. This is a famous collection of test functions for unconstrained optimization problems. This collection was introduced by Moore, Garbo, and Gilstrom in 1981. We have I have the results here. I want to go to details here. Just let you have a look. Just to compare the two sides: standard implementation, adaptive implementation. Compare. Look at the needed number of function evaluations. Compare them, and also compare the final objective value, right? So that we can see this table for these three test functions. The new implementation performs better when the dimension is higher here. Now the second table, we can see perhaps even more illustrative. Look at this is called penalty 1, the first penalty 1 function. Now n equals 60. After this many function evaluation, we still have this objective value 10 to the +6, not -6. That's different. And for the new implementation, we also did a large number of function evaluations, about 250,000 here. But we're able to get a good approximate solution. So that's good news for the new implementation. And similarly, we have some more results on some other test functions. The last table. Rosenbrock is here. Rosenbrock, this is extended Rosenbrock. We can see, even though we don't have a lot of function evaluations here, because Rosenbrock in standard implementation it terminated prematurely. Look at the objective values. The minimum objective value is 0. They are still far away from the solution. In the new implementation, in each case we were able to find a good very good approximate solution. But we see the large number here, about over 100,000 here, right? So that's some. We we did some investigation why for Rasenberg, look at I did not even choose 60 here, because this Rasenberg function is difficult for the new implementation. It's a difficult one. Turns out, when we tried, turns out for the new implementation, even for new implementation on the Rasenberg function, it still uses too many reflection points. So one future research direction is to reduce the use of the reflection step. That's a research topic. I want to summarize what we have done today. So we first talked about the performance of the standard Nelder Mead Simplex method deteriorates as the dimension of the optimization increases. We also discussed expansion and contraction steps have decreased the objective value, but not the reflection step. Large simplex helps decrease the objective function value. Implementation using adaptive parameters is promising for higher dimensional problems. Here are some future research problems. Study the convergence properties of the original Nelder method for dimension bigger than equal to 3. This topic is related to Jianhong's suggestion earlier, how to set up a suitable initial simplex, right? Oh, okay, yeah, Professor Xiao, right?
Yeah.
Okay. How to set up good, suitable initial simplex. That's indeed important. A suitable and good one can make a big difference. But how? That's the research question. How to effectively reduce the use of reflection steps? This is another research topic. Last, this is in high demand. Devise a new derivative-free method for high-dimensional problems. Not just modify the simplex method. Some other ideas. This is in high demand. And references here. Thank you.
We're grateful for the talk. Does anyone have questions?
Do you have any feel for how the rate of convergence depend on the initial complex?
How
The rate of convergence depends
rate
on
of convergence.
The initial.
It definitely depends on the initial choice. In the talk I gave here, by the limit definition, that it becomes kind of irrelevant. If you look at the limit definition here, that here, if we take a limit, so it affects this. But how this does not, I wrote this down. I still definitely affects the answer, but it's not clear to me how now, at least for this moment.
So there's not like a basin where on that initial complex you get the same rate.
Which means
Are they locally constant, you think, or no?
You mean for
The rate.
for the rate, right? For the rate
Yeah.
for different x0, then we
Yeah.
it's
Not
okay,
clear,
yeah.
yeah.
This is later on. This rate is a numerical rate. Yeah, this is numerical rate.
Mhm.
It's not a theoretical
Theoretical.
rate. So yeah, it's not fully understood. Yeah.
I just feel it's kind of counterintuitive because the reflection step is one of the important steps to help the synthesis to move around. Because initially, chances are you're not going to just frame the minimizer. You use reflection as one way to move the simplex around. So why it will make the whole thing worse instead of getting things better?
That's good question. If you look at this, if you look at one slide here, if you look at this theorem, actually, we have that here, right? If you look at this theorem, this is always one. This modulus is always one for reflection. This is already indicator. If you have always one, a combination of you may make a little progress, but you don't expect this will reduce the more the simplex vertex decay faster to the minimizer, right? If by this condition, this is already indicator here, I think. But the later slide, so basically in the new recent paper, we were able to prove this theorem. We proved the theorem of this one. But this one, for reflection, we don't have the so-called sufficient decrease. The sufficient decrease is not active. And numerically, we can see, indeed, we do see, we use too many reflections, right? Too many reflections when dimension is higher. That's half theory, half computational explanation.
For your adaptation algorithm, you use the n as adaptation. Now the size, I know when you go to your adapted, the formula there. When you use this, because now it looks like when the dimension increasing, you enlarge your simplex size.
This one, not the expansion. These two, yes. We keep a bigger, This is contraction. This is a shrinkage. Yes, these two parameters will keep the next simplex bigger. But this one actually, if you look at this, not that case because this is the expansion, right? This is if n is bigger, this is 1. This one is 2. So the expansion step, I don't expand too much. I'm more conservative to do a smaller expansion.
I'm wondering just the coefficient is just, I know when you try to make it, you look at it consistent with n equal to 2. Now is n equal to, I don't know, is that coefficient is essentially the characteristic or just be arbitrary pick in that way?
This one or here?
So for example, like n over 2, because you pick 2 on the
2
top.
over n?
Yeah, 2 over n equal to 2, you get 2, so you're consistent with n equal to 2 situation.
That's one reason we picked 2 over 1. We also tried 1 over n.
Oh, you also tried?
Yeah, we also tried 1 over 1. The results, it depends. The results are mixed.
Oh.
When we try the base equal to 1 over n, then in that implementation, it performs better than this one, but sometimes worse. So it's a mixed result. So we use this. Particularly, you are right. That's a major consideration. One of the major considerations we use 2 over n. And also, if we put this 1 over n, the expansion is even smaller, right? So we still want a little bit bigger expansion than 2 over n, our choice.
Expect the subject to start from exhausted, but it may be time to invite everyone to join us up for some specs in the math library and to thank the speaker again.